Welcome, everyone. Today we are taking an inside look at the architectural innovations coming with the Go 1.26 release. This version, scheduled for February 2026, marks a major milestone in high-performance Go development. As illustrated in our technical schematic, we are introducing direct support for advanced SIMD instructions, including an AVX512 register array and a specialized Intrinsics engine for Neon and SSE4. These additions allow for massive parallel data processing directly within the Go runtime. One of the most exciting features is the new Greentea garbage collector. By implementing a sophisticated memory arena that leverages concurrent sweeping, parallel marking, and ultra-low latency barriers, we are significantly reducing GC overhead for mission-critical applications. From the 1024-bit data bus to optimized power management, Go 1.26 is engineered to push the boundaries of performance. This release is built to ensure that Go remains the premier choice for high-concurrency, high-throughput systems. This slide illustrates a significant shift in the Go ecosystem regarding SIMD, or Single Instruction Multiple Data. Prior to version 1.26, SIMD optimizations were strictly internal to the standard library. While the Go runtime utilized these capabilities for performance, they were effectively locked away from developers, making them inaccessible for use in external application code. With the release of Go 1.26, we see a pivot toward exposed primitives. SIMD instructions are no longer restricted to internal runtime use. They are now being made available to user code through an experimental SIMD hierarchy. This change empowers developers to write high-performance applications by leveraging hardware-level parallelism directly within their Go programs. The concept of the assembly tax explains why achieving high performance historically came at the cost of high maintenance. There are three primary frictions involved. First, assembly is opaque to the optimizer. Because assembly files are essentially black boxes, the compiler cannot perform critical optimizations like inlining, which limits the efficiency of the surrounding code. Second, there is a significant maintenance burden. Writing assembly requires manual register allocation and provides no type safety, making the codebase fragile and difficult to evolve. Third, we see high overhead, where function call costs can actually negate any performance gains, especially in small loops. As the diagram illustrates, inserting a heavy assembly block into the flow of code execution creates a point of high stress, introducing structural friction that often outweighs the benefits of hand-optimized code. Introducing the SIMD/Arch SIMD package, an experimental toolset designed to facilitate direct compilation to specific SIMD instructions, including AVX512 and Neon, without requiring manual assembly. This workflow is shown here through the use of compiler intrinsics. When a developer uses a function such as avx2.addFloat32, the Go compiler recognizes it as an intrinsic and performs a direct emit. This results in the immediate generation of the corresponding CPU instruction, such as vpad-d using YMM registers, optimizing performance by bridging the gap between high-level code and hardware execution. The core philosophy driving Go 1.26 is a shift toward prioritizing performance over portability. By adopting a bottom-up approach, we are providing library authors with the tools they need to achieve maximum efficiency. As shown on the balance scale, the emphasis is placed on performance and control, allowing for the creation of optimized kernels tailored specifically for target hardware. This level of optimization requires a deliberate trade-off. It necessitates maintaining distinct code paths for different architectures, such as AMD 64 and ARM 64. While this moves away from immediate, universal portability, it empowers developers to unlock the full potential of the underlying hardware for their most demanding applications. Single Instruction Multiple Data, or SIMD, is a parallel processing architecture that enables a CPU to perform the same operation on multiple data points simultaneously. In this visualization, we observe 8 individual 32-bit floating point values, labeled data 0 through data 7, entering a single processing lane. Rather than executing 8 sequential instructions, the processor applies a single addFloat32 instruction across all data points at once. This operation generates 8 distinct outputs, result 0 through result 7, in parallel. By processing 256 bits of information within a single CPU cycle, SIMD significantly enhances performance and efficiency for data-intensive workloads such as signal processing, multimedia encoding, and large-scale mathematical computations. To maximize performance while maintaining broad compatibility, we utilize a hybrid approach centered on runtime detection. This strategy ensures that software remains safe and functional across various hardware architectures without sacrificing performance. Looking at the flowchart on the left, the logic is straightforward. At execution time, the application checks for specific hardware features, such as AVX2 support. If the hardware is capable, the system invokes an optimized kernel designed to leverage those specific instructions. Conversely, if the feature is absent, the execution branches to a generic fallback, ensuring portability across different systems. The code snippet on the right demonstrates this implementation in practice. Within the .product function, we first perform a runtime check. If supported, we return the results from the optimized AVX2 path. Otherwise, we fall back to a standard portable version. This methodology allows us to provide the best of both worlds: peak efficiency on modern hardware and reliable fallback mechanisms for older or different environments. In this deep dive into the anatomy of a hot loop, we examine how SIMD instructions, specifically AVX2, are utilized to maximize computational performance. The code snippet on the left demonstrates a loop that iterates in chunks of 8 rather than processing elements individually. This aligns with the 256-bit width of YMM registers, which can accommodate 8 32-bit floats simultaneously. By employing specialized load functions, we pull contiguous blocks of data directly from memory into these registers. As highlighted in the bottom right, these operations are highly efficient because they compile down to the vmov_up_us assembly instruction rather than a standard high-overhead function call, ensuring zero allocations. The diagram illustrates this parallel load process, showing how 8 distinct data points are moved from a memory block into a single YMM register in a single operation. Once the data is loaded, vector arithmetic is performed. Here, we see a multiplication followed by an addition, which forms the basis of a dot product or similar calculation. By operating on entire vectors instead of scalars, we significantly increase throughput and hardware utilization, allowing the processor to execute more operations per clock cycle.
When we examine the anatomy of a hot loop optimized for SIMD, two critical components emerge: reduction and tail handling. In the code snippet, we see a vector reduction operation that collapses multiple parallel lanes into a single scalar total. This is represented by the funnel diagram, which illustrates how values from a vector register are aggregated into one result. However, because datasets are rarely perfect multiples of the vector width, we must account for the remainder. As shown in the data slice illustration, while the bulk of the data is processed in 8-element SIMD blocks, the final 3 elements do not fill a complete register. These are handled by the tail loop using standard scalar processing. This dual approach ensures that we maximize hardware performance while maintaining mathematical correctness across the entire dataset.
Inlining offers several significant performance benefits, particularly when implementing low-level operations like the AVX2 addition shown here. One of the primary advantages is the elimination of boundary costs. By removing the overhead of traditional function calls, the compiler can perform optimizations across what would otherwise be rigid function boundaries. Furthermore, inlining facilitates better register preservation. This ensures that variables stay within the registers for as long as possible, effectively avoiding the latency associated with stack spills. Lastly, this approach preserves type safety. The arithmetic logic remains fully type-checked by the Go compiler, providing the reliability of a high-level language without sacrificing the speed of specialized hardware instructions. The Greentea garbage collector represents a major internal win for the Go language, offering a performance boost that benefits every developer automatically with no code changes required. Its primary mechanism involves leveraging vector instructions to scan memory pointers in parallel, processing between 4 and 8 words at a single time. As a result, the garbage collector's mark phase is significantly faster, leading to a noticeable reduction in stop-the-world pauses. This feature is enabled by default, though it can be disabled for debugging or comparison purposes by setting the environment variable goExperiment equals no Greentea GC. Let's look at the roadmap toward portability for SIMD operations in Go. With version 1.26, we are establishing the necessary foundation through low-level primitives in the SIMD and ArchSIMD packages. At this stage, the implementation requires distinct code paths for different architectures, such as AMD 64 and ARM 64. While these primitives require more manual effort, they are the essential building blocks for our future high-level API. Looking ahead to Go 1.27 and beyond, the goal is to introduce a portable API centered around the vector T type. In this evolution, the compiler will handle the complexity of the hardware layer by automatically selecting the optimal instruction set for the target environment. This transition ensures that the foundational work being done now will eventually enable a more seamless and architecture-independent development experience. Moving to our summary and recommendations, we have specific guidance for different roles within the community. For app developers, no action is required. You can simply enjoy the benefits of the faster Greentea GC. For library authors, we recommend porting your assembly routines to Arch Simd to ensure greater safety and easier maintainability. Ultimately, Go 1.26 represents a mature and significant step toward high-performance computing for everyone. We encourage you to code responsibly, as the power of optimization is now in your hands.